In this tutorial, I'm going to have a look at the IEEE 754 floating point standard. IEEE 754 is a means of representing floating point numbers in binary. We're going to have a look at the single or float 32-bit and also double or 64-bit precision. I'm going to use some worked examples with the single precision. I'm only going to briefly touch on the double precision because it's just bigger. The process is identical in all other regards. Representing numbers. So, if we have a denary number such as 0.101, we can also represent this by shifting the numbers so that they are 1.01 and then multiplying that by 10 with an exponent of -1. Or what this means is that if the number is actually 0.101, then to represent it as 1.01, we've effectively multiplied it by 10. So to get back to that original number, we need to divide by 10. And 10 to the power of -1 is the same way as writing 1 over 10. If I have a bigger number like 128, and I want to store it as 1.28, then effectively I've divided it by 100, or divided it by 10, and then divided it by 10 again. So to get back to 128, I'd need to multiply by 10, and multiply by 10 again, or multiply by 100, which is the times 10 to the power of 2. Now, representing these numbers where you have a single digit as the whole number component, and that number being between 1 and 9 inclusive, this is called normalized scientific notation. And that's what we're going to be using with IEEE 754 when storing binary numbers. So this is the layout of single precision IEEE 754, and it is in fact exactly the same for the double precision. All you're looking at is having more bits that you can store these numbers in. Now the first part is the sign. So it's a 1-bit flag to say if it's positive or negative, and it is a 0 for positive, 1 for negative. When you're looking at that, you might think, oh, hang on a second, positive should be 1 because that's true, and but that's not the way it works. In actual fact, this does work the same way as the signing in 2's complement, so at least it's the same as that. But just remember, 0 for positive, 1 for negative. The exponent. So in single precision, you've got 8 bits to store the exponent. So this is the part where you have the to the power of 2 to the power of -3. It's that 2 or -3 power that you've got. That's what that exponent is. And the way that we need to store it, because we need to deal with positive and negative exponents, we have to bias it because we need to store this as a positive number. So with 8 bits, the smallest negative we could store is -127. So we simply add 127 to this number. And that ensures that we've always got a positive number stored there. Obviously with the double precision, the number's different. I'll go over that later. And then the fractional component. Now I don't myself remember or commit to memory the number of bits for these. I simply remember the sign is always 1 bit. In single precision, the exponent is 8 bits, so I've got 9 bits. I know it's 32 bits, so 32 minus 9 gives me the 23. Okay. Okay, worked example. So we want to store 1.25, that's a denary number, using IEEE 754. So the first step is we actually need to convert the number into binary, and I'm going to use the multiply by 2 method to convert the fractional component. So the way that you convert fractional numbers is you actually convert the whole number component and then you convert the fractional number component and you bolt them together. Because the whole number component here is 1, it's identical in denary and binary, so I'm not going to bother with that step. But to convert the 0.25, what you do is you use the multiply by 2 method. So 0.25 multiplied by 2 gives us 0.5. The whole number part of that is 0, so you write 0 down. 0.25 times 2 gives you 1.0. The whole number component of that is 1. At which point you can stop, because we take the 1 away from 1.0, we're left with 0.0. There's no fractional component remaining. So you actually take them top down in this method, which is different to the whole number conversion where you take the number bottom up. So in this case it becomes 1.01 in binary, and I've written the exponent, so we're multiplying by 2. It's already in standard scientific notation here, so you don't need to shift the number's position at all. So the exponent is 0 in this case. Okay, so we've got 1.01 in binary, exponent of 0. How do we represent this? Well, the first thing is the number is positive, so we put the sign in, which is going to be a 0. The second thing we need to do is we need to store the exponent. To calculate that, we need to add the bias. The bias is 127. The exponent is 0. 0 plus 127 is 127. You then got to convert that into binary. There's a quick trick for certain numbers. 127 is actually 1 less than 128, and 128 is the value of the 8th position in binary. So you're 1, 2, 4, 8, this is from the right hand side. 1, 2, 4, 8, 16, 32, 64, 128. Because it's 1 less than 128, it's a 0 or no 128s, but it's a 1 in every other column. Put the number in. The fractional component is the 0, 1. And you literally write 0, 1 and then pad the remainder with zeros. If you've got leftover values, just pad them out with zeros. Obviously, if you had a number that exceeded the fraction, you'd get some sort of overflow. But in this case, most of the examples I've seen, you won't worry about that too much. Second example, so we're going to store 0.5 in base 10 using IEEE 754. So 0.5 times 2 gives us 1.0. Take the 1, and that's what we're left with. So it's 0.1 in binary. The exponent there is 0. We want to represent this normalized, so 1.0 times 2 to the minus 1, because we had to shift 1 column over. So here we go. 1.0 times 10 to the minus 1. It's a positive number, so you put a 0 in. Exponent is minus 1 at the 127, gives you 126. Again, just like the 127, only we've taken 1 off of it, so the far right digits change from a 1 to a 0. Put that in as the exponent. Fraction is all zeros. It was 0, literally just pad it through, and that's example 2. Third example, I've put in a larger whole number, so 24.75 in binary. So first thing to do is just to convert the whole number. So convert 24 using the divide by 2 method. 24 divided by 2 is 12, no remainder, so it's a 0. 12 divided by 2 is 6, no remainder. 6 divided by 2 is 3, no remainder. 3 divided by 2, well, it goes in once, remainder 1, so the remainder comes out. 1 divided by 2 doesn't go, remainder 1, leaving us with 0. And you can check that number. It's 11000, so that is no 1s, no 2s, no 4s, an 8 and a 16. 16 plus 8 is 24. Convert the fraction number to base 2 using the multiply by 2 method. So now we've got the 0.75. Multiply that by 2 gives us 1.5. Remainder, sorry, not the remainder. The whole component there, the whole number component is 1. Take that out, we're left with 0.5. 0.5 times 2 gives us 1. Again, whole number part is 1. So the 0.75 is represented by 0.11 in binary. You now bolt the 2 parts together, so we've got 11000 representing our 24, 0.11. So now that's 24.75. Exponent in that case is 0, but it's not in normalized form. So to get it in 1.1000011, what we've had to do is we've divided the number 1, 2, 3, 4 times, which means that to get back to the original we'd have to multiply with an exponent of 4. And so here we are, 1.1000011 times 10 to the power of 4. It's a positive number, 0 goes in. The exponent, again, 4 plus 127 gives us 131. We've now popped over the top, so we need that 128. It's actually 128 plus another 3, which is a 2 and a 1. This is why we've got 1,000,0011. Pop that in the exponent, and in the fraction is the 1,000,11, and then pad the remaining zeros. There's 3 examples on the single precision. Hopefully that sort of clarifies how to do these. Obviously, if you're working backwards the other way, you just reverse the steps. Look at the sign, you know if it's a positive or negative number. Pull the fraction out, add 1 to it, so it becomes 1 point whatever's in there. Convert the exponent by subtracting 127, convert it first from binary to denary, take off the 127. Whatever you're left with is the number of positions you need to shift the numbers while holding the radix point in place, or in fact the decimal point in that case. Double precision, pretty much identical. 1 bit to represent the sign, 0 or 1. Exponent is 11 bits. So we've gone from 8 to 11. Again, because you know it's a 64-bit number, you can do 64 minus 12, so you should be getting 52 bits for the fractional component. And the process is the same as you do for the single precision. The only difference is that instead of the bias being 127, because you've got 11 bits rather than 8, the bias is 123 that you need to add or subtract depending on which way you go. So I hope that's been helpful. Key of these is obviously to practice.